Welcome to Kitchen Table Electronics, Lesson 5.2 AC Circuits Capacitors. So now you have built and tested your home lab and you are ready to carry out advanced physics lab experiments on your kitchen table. So the irony is we are now going back to the beginning of a basic advanced physics lab class, but the good thing is you already know digital electronics, computer programming, and how your equipment works in a way that students starting a conventional upper division physics lab like this would not. So you're way ahead of the game. Okay, let's get down to the gory details of AC circuits, and these will occupy the next several modules. Capacitors. So here is the symbol for a capacitor, a pair of parallel plates. It's shown here with a gap between the plates, so a current can't flow from one lead to the other, and indeed we know that capacitors block DC but pass AC. So let's therefore take a look at how AC currents flow. When a voltage is applied across these plates, an electric field is set up between them, and in consequence these metal surfaces then have a surface charge related to the intensity of the electric field between the plates. If you then change the voltage across the capacitor, the surface charge will increase or decrease depending on whether you increase or decrease the voltage, with the result then that charge will flow into or out of these leads, not across the capacitor but into or out of these leads. This time-dependent polarization charge is the AC current that passes through a capacitor. Here's the defining equation for a capacitor. The total charge stored on these plates is given by the capacitance times the voltage. The units of capacitance are the farad after Michael Faraday, and 1 farad stores 1 coulomb of charge when a bias of 1 volt is applied across a capacitor. Here are some examples of capacitors. For the very largest values which by the way do not begin to approach a farad in most electronic applications, but may be hundreds or even thousands of microfarads, such capacitors are typically polarized capacitors, shown here with these stripes on the outer case that show you the way in which you should wire them. They're made by anodic oxidation of aluminum foil, and so if you apply the bias the wrong way round so as to electrochemically reduce this oxide on the surface of the aluminum, the capacitors will short circuit and blow up. So pay attention to this bar, which generally points to the negative side with a large minus written on it. These little things here, these disc-like things, are ceramic capacitors. They have the advantage that they have very little intrinsic inductance, and we'll talk about inductance later in the coming modules, which means they have a very rapid response to changes in voltage. However, their quality is not so great in the sense that a DC current, a very small one albeit, can pass through them. In contrast, mylar capacitors have a very large internal resistance. No DC current will pass through them, but they have a reasonable amount of inductance associated with them, so their response to rapid changes in voltage is not quite so good. Now, it's mylar capacitors we're going to be using largely in this course, and here is an image of one such. The bad news is that their values are not terribly easy to read. Now, in general, for the capacitors we'll be using, they all follow the same convention, but this is not universal. So A, check with Google, and B, when you buy capacitors, I suggest you store them in a baggie with a little label saying what their value is. You'll see later in this series of modules that I think I picked up a capacitor and misread its value at some point. So the notation for capacitors of this sort is that this is the value in picofarads with the following convention. The first 2 digits are the numerical values of the capacitor. The third is the exponent of 10. So this is the value in picofarads, then 68 times 10 to the power 3 picofarads, or 68 nanofarads, which is 0.068 microfarads. I've gone on here to show you a derivation of the formulae for capacitors in series and parallel. I don't think you'll ever use this to make practical capacitors for an electronic circuit. You'll just buy the right values. But it's good to know these formulae because in electronic circuits, stray capacitance, often in parallel with, for example, the input of your operational amplifier, will affect its performance. So it's good to know how parallel capacitors add together. Meanwhile, series capacitors can occur because, for example, your oscilloscope lead can break, giving you a tiny capacitance in series with the internal capacitance in the oscilloscope. So for these reasons, it's good to know these formula. Plus, we're going to use them anyway because I'm going to give you a lab to do in which you put capacitors in series and parallel. So let's just very quickly derive the results. So two capacitors in parallel with a voltage V applied across both of them. The charge on each capacitor, of course, depends on the capacitance according to this formula. The total charge is just the sum of the charges on the two capacitance. So Q total is Q1 plus Q2. We divide by V. Q total over V is Q1 over V plus Q2 over V, i.e. the total capacitance, Q total over V, is C1 plus C2. When we put capacitors in series, both capacitors share the same charge. They must do, otherwise current would flow in this connecting wire in the middle. So the total capacitance now is Q. The total voltage is V1 plus V2. And so if we divide all of this by Q, V over Q is V1 over Q plus V2 over Q, we see that V over Q is 1 over capacitance. Go back up here to this formula, divide both sides by Q and both sides by C. V over Q is 1 over C, so 1 over C total is 1 over C1 plus 1 over C2. This looks like the formula for resistors in parallel. Putting capacitors in series reduces their value, putting capacitors in parallel increases their value. Now let's take a look at the relationship between current and voltage in a capacitor. Here is the defining equation for capacitance, Q equals CV. If we take the time derivative of both sides, we have dQ dt, the number of coulombs per second, which is the current flowing into or out of the capacitance, is C dV dt. Let's take a concrete example. Let's take V is some amplitude V0 sine omega t. Remember, omega here is the angular frequency, or 2 pi times the frequency. So here is this function plotted. It starts at 0, it goes up to V0, back through 0 and down to minus V0. The time derivative of this is taken by remembering that the derivative of sine theta is cos theta, and the derivative of omega t with respect to t is just omega, so the derivative of sine omega t with respect to t is omega cos omega t. Keeping the V0 and putting the C in to get the current, C dV dt, we have I is omega C V0 cos omega t. So the current there is like cosine omega t, and that's this red dashed line plotted here. You see that current peaks 90 degrees before voltage. This is because the current is maximum when the slope of the voltage with respect to time is maximum. When this curve turns over here at the top, the change of voltage with time right at the top is 0, and so the current is 0. And then here the current is going negative, or the voltage is going negative at a high rate. Here it's back down to 0 again, and so on. And so you can see how the current follows as the cosine of omega t when the voltage is varying as sine of omega t. Now if we just forget for a moment about this interesting phase relationship between current and voltage, and so let's just throw this sine and cosine term out and just look at the relationship between I and V, ignoring the phase, and rewrite this in the form of Ohm's law, V equals I times R, you see that the equivalent of R here is 1 over omega C. V is current over omega C. And this leads then to a quantity we call the capacitive reactance. Xc is 1 over omega C. It has units of ohms, and it tells you in effect what resistance a capacitor applies to an AC voltage of frequency omega. Just a word of caution here, I'm using the physics convention later on of I for the square root of -1, so from context you'll have to be careful to note when I is a current and when I is the square root of -1. Capacitors are called reactive components because current and voltage are not in phase. Resistive components have current and voltage in phase. In a capacitor we see that current lags voltage by 90 degrees. Right, we're going to measure some aspects of capacitors' response in circuits, and so we will bring out our trusty AD9850. At this point you may want to make a note of the time of this video and get out of it and revise lesson 2.1 and then carry out the experiment I'm going to describe now. The 9850 was not developed as a signal generator per se, and so it has a fairly high internal Thevenin resistance. Once again, refresh yourself by going to lesson 2.1. What this means is you cannot put a very low resistor as a load across the output of the AD9850. How big should the resistor be? Well, you know what you need to do. Determine the internal Thevenin resistance of the 9850. To do this, I suggest measuring the voltage output with your O1 scope. So measure the peak-to-peak voltage, make sure that you have the scope AC coupled so that this measurement is accurate. And then put a 1 kilo ohm load across the output between the output and ground, and look at the little drop in V peak-to-peak that occurs. You should then be able to use the math from lesson 2.1 to calculate the Thevenin internal resistance of the AD9850. You'll see that it's quite a reasonable number of ohms, but it's not so much that a 10 kilo ohm resistance will have any significant effect on the output of the AD9850, and I urge you to test this for yourself by putting a 10 kilo ohm resistor across the output and ground and seeing that you can barely see any sign of a voltage drop with a 10 kilo ohm load. Good, well I hope you've done this exercise and have now returned to this video and you're ready to measure the response of a capacitor, and we know we're going to use 10 kilo ohms as a sensing resistor in the case when any significant fraction of the load appears at the AD9850. So here's the circuit, here's the AD9850 with the signal out and ground. We have a capacitor and we've inserted in series with the capacitor a current sensing resistor. We've had to do this because we need some means of turning current into voltage in order to see it on channel 1 of our O1 oscilloscope. Channel 2 is connected across the whole circuit. Now we want to be in a limit where most of the voltage is dropped across the capacitor. Remember the capacitive reactance is 1 over omega C. So if we make C very small and omega very small, then we can make 1 over omega C very big, and it means most of the voltage will be dropped across the capacitor. So we will set our 9850 frequency to 400 Hertz, and we will choose C as just 330 picofarads, marked 331. So small c, low frequency, high capacitive reactance, and hopefully our 10 kilo ohms will then be pretty negligible in terms of changing the voltage across the circuit. Because I've chosen these values for this reason, you'll want to set channel 1 to 5 millivolts per division, because the voltage that will appear across this resistor will be pretty small. Alright, here we go. Here's a screenshot of what I got on my O1 scope. Now you'll see channel 1 and channel 2 are DC coupled. These are the zeros for them. You see that channel 2 is set to half a volt per division, so 1, 2, 3, 4, maybe 5 divisions, about 2.5 volts coming out of the AD9850. 5 millivolts per division, and maybe 1, 2, 3 divisions, so about 15 millivolts across that resistor, so good. Most of the voltage is dropped across the capacitor. And indeed, you see that the current through the circuit, as measured by the voltage across the 10K resistor, lags the voltage applied to the circuit by about 90 degrees. Here's one full cycle here, and this distance here is about a quarter of that. Now, what happens if we aren't so careful about making sure that most of the voltage is dropped across the capacitor and not the resistor? So now what we're going to do is increase the capacitor to a much larger value, 220 nanofarads. And remember, the capacitive reactance is 1 over omega C. So we've increased omega C now by a huge amount, by a factor of 1,000. And we're going to increase the frequency by a huge amount to 20 kilohertz from 400 hertz. And when we do that, we see now that the voltage across the resistor, this red curve here, is almost equal to the applied voltage. In other words, the capacitive reactance is negligible compared with the resistor, and because resistors have current and voltage in phase, that's what we see on our O1 scope, that now the current is very nearly in phase with the applied voltage. Very nearly, but not exactly. You'll see if you look at the advanced topic, the math for this class, that the tangent of the angle between current and voltage in a circuit like this, tan phi, is given by 1 over omega RC, and this still is not quite large enough to have these two lined up. Okay, back to this quantity of reactance, where we put our hands over our eyes and just said, let's ignore the sine and the cosine. We know that in this RC circuit, because the reactance of the capacitance goes like 1 over omega C, that at low frequencies the capacitor dominates, and at high frequencies the resistor dominates. We've just seen this. Of course, the units of capacitive reactance, because they relate current to voltage, must be ohms, but we're stuck with a mathematical problem now of how do we plug in the phase change. What makes a sine become a cosine? The answer is to use complex algebra, and now we use the symbol I to represent the square root of -1. And you will see, derived in the advanced topics, that the way to include this phase shift for sine waves is to define a new quantity now, which behaves just like R in Ohm's law, V equals IR, or X in V equals IX, but now includes the phase in V equals IZ, is to put into Z a factor I. And for a capacitor, it's 1 over I, or if we multiply top and bottom by I, minus I over omega C. Why does this work? Well, if the applied voltage is purely real, sine theta, and lies therefore along the horizontal axis in a diagram like this, where we plot complex numbers on the vertical axis, then including this factor of minus I will then shift the phase of the current with respect to voltage by 90 degrees. Once again, this is discussed further in the advanced topic mathematics for this class. Let's end by looking at a couple of circuits that do something interesting and useful, the integrator and differentiator. So here once again is the Q equals CV time derivative expression that I is C dV dt. So you can see that the current through a capacitance, if you can measure that without disturbing V, is given by the time derivative of the voltage across the capacitance. In order to achieve conditions in which the voltage across the resistor changes by a very small amount with changes in current, we need a small resistor. And in order that this resistor is small relative to the capacitive reactance, we need a tiny capacitance. So to make our differentiator, we are going to choose 100 picofarads, 101 for the capacitor, and a 100 ohm resistor for the current sensing resistor. But we're also going to make an integrator, because you can see if I rearrange this equation, I dt is C dV, and then integrate both sides, I end up with V is 1 over C integral of I dt. So in other words, the voltage across the capacitor measured here will be the time integral of the current flowing through the capacitor. If we make the voltage across this small by having a large capacitance now, notice the capacitance is what we're measuring the voltage across, so a large capacitance, then in that case we will have, if we apply a constant voltage here, a constant current here, and the integral of a constant, of course, is a time increasing linear ramp. Now in both these circuits we've had to be a little bit fussy about our component values in order to get a perfect differentiator or a near perfect integrator. It probably won't come as any surprise to you to learn that there are tricks you can play using operational amplifiers, just as you turn an imperfect diode into a perfect rectifier using an op-amp, so you can use negative feedback to make perfect differentiators and perfect integrators. If you ever need to do that, do a Google search. We're going to stick with doing it the simple way in this module. We have one other issue to deal with, at least I did. My AD9850 board did not come with a square wave output as promised. I guess the manufacturer never connected the pin, and so I had to find another source of square waves. By the way, I should say why we want square waves. It's because the integral and derivative of a sine wave is just a cosine wave, or a cosine wave is a sine wave, and that's not terribly interesting to look at on the scope. The integral and derivative of a square wave is interesting. So for our source of square waves, I'm using the calibration signal that is output on these little tabs on the O1 scope. It's 5 volts at 1 kilohertz. I've taken that here. This is my differentiator with a 100 picofarad capacitor, 100 ohm current sensing resistor, and this white lead goes to the second channel on the scope. The first channel is connected here and measures the voltage across the whole circuit. So let's take a look at this differentiator using the 100 picofarads and measuring the current through the circuit by measuring the voltage across the 100 ohm resistor. Channel 1 is set to 5 volts a division, and it's DC coupled, so it's going between 0 and 5, 5 to 0, and so on. Channel 2 is set to 50 millivolts per division, and it's also DC coupled. Now the derivative of a constant voltage time derivative is of course 0, and that is the output here. At this point the voltage goes crashing down to 0, and the derivative of the voltage versus time here is effectively minus infinity, or a negative going delta function. Now the AD9850 cannot supply infinite current, and the scope doesn't have infinite time response, so the result is a spike that goes in a negative direction. Now the voltage is constant at 0, and so the output stays constant at 0, and then at this point the gradient becomes plus infinity, and here is a positive going delta function. We've made a differentiator. This is not only fun, this is a circuit that you might use to trigger digital timing electronics. What about the integrator? So now we're going to use the 10 nanofarads and the 10 kilo ohm resistor, and now we're going to be measuring across the capacitor in order to get our integration function. So now we're measuring the voltage across the capacitor, which gives us the integral of V dt times 1 over C. So when the voltage is held constant at plus 5 volts here, then if the voltage across the capacitor is very small, a constant current will flow through this fixed resistor into the capacitor, and the result will be an increasing voltage with time across the capacitor as charge accumulates on the capacitor. We then switch back to 0 voltage, and the capacitor now discharges at a constant current, and so on, producing a triangle wave. If you look carefully, you'll notice this wave is not exactly a triangle. It's bending over and flattening out just a little bit with time here. This is because the decay is actually an exponential function, and we're sensing slightly the change of voltage through the resistor as the capacitor charges up and charges down. Okay, you've learnt how to make a differentiator, you've learnt how to make an integrator, and you've learnt about the idea of capacitive reactance, and you also understand the units of capacitance and how to calculate these quantities. So let's turn next to the more general case of NER NEC, any frequency, and find how circuits respond.